Okay, today we're going to talk about electric potential, okay, and electric potential energy, which is makes use of the electric field. Up to this point, we've been studying the electric field kind of in a vacuum. Okay, we can see where it's involved with force, but we don't really see some of the use for it. It really comes in handy when we start studying electric potential, because we can start looking at the forces. Not only the forces, we can look at the velocities of charges as they move in and away from each other. Okay. Now, a very important aspect of the electric field is that it is a conservative field, and the fact that it's a conservative field allows us to look at potential energy. Okay, which means that along any path we're going to get similar results, and that's very important and very helpful for our understanding of this topic. Okay. Now, first of all, let's talk about changes in potential energy in general. If we're talking about gravity, okay, let's say I take a nice little handy object here, my Expo whiteboard Care. Okay, I take this and I lower it down. Okay, now think about this. What happened to the potential energy of this as it lowered down? Okay, potential energy decreased. Now let's think about the work that's done by gravity on this. Okay, as this is lowered down, the force of gravity is down, the direction of motion is down. Okay, so our angle between the two is zero. Okay, so what we get is that the work done by gravity is positive, but the potential energy change is negative. So when something moves down from an initial spot to a final spot, we're talking about potential energy due to gravity. Okay, I've got a positive work done by gravity, but a negative change in potential energy due to gravity. Conversely, if it goes from down to up, okay, I take my Expo whiteboard cleaner, I raise it up, okay, the work done by gravity, okay, the force is down, and the direction of motion is up, okay, so that gives me negative work, but we know that the change in potential energy is positive. Okay. Now, thinking about the force, okay, potential energy due to gravity is mgh. Okay, the force of gravity on this is mg. If I raise it up, the change in height here is h. Okay, so what we can say here is that the magnitudes are going to be the same. The work done by gravity is the force mg times the change in height. Well, the change in potential energy is mg delta h. We already know that. So now, one thing that we can say here is that the change in potential energy due to gravity is equal to negative the work done by gravity. Right? Well, now we're going to extend that concept to the electric field. Okay? Let's say, I'll use nice shiny blue. Say that my electric field is pointing to the right here. Here's my E field. And I take a point charge in that field, and I move it along here like this, some distance d. Okay. And this will be q positive. Okay. Well, now the work done on this charge by the electric field will equal the force on that charge q, times the distance. Well, now the force on that charge q is equal to EQ times that distance d. And a lot of times we'll see this as the work done by the electric field is equal to Q times the electric field times distance d. I don't know why I wrote it in that direction before. QED is fine. Okay? If you're a Latin person, that's kind of a if you take the Latin language, okay, QED has some very specific meaning, but it's not the same thing as this. Okay, so the work done by the electric field here is going to equal Q times the electric field times D. Now, the change in potential energy then is equal to negative Q E D. Okay, so it's something that we can see here, okay, how the work done by the electric field and the change in potential energy, okay, are related to one another. Okay, because we know that the change in potential energy is equal to negative the work done by that field. So now, something we want to talk about here is reference points. Okay. One reference point that we want to take a look at, we want to set someplace up to equal 0. Okay, now, when we do potential energy due to gravity, we do this, okay? We set 0 to be some height, okay? It might be, if I'm dropping it like this, it might be the surface of this desk. Okay, if I drop it over the ground, it could be where the ground is. Okay, it could be sea level, it could be wherever the ground is, it could be the roof of a building, because that's going to be the lowest point. So usually make the lowest point 0. Okay. Now, when we talk about reference point for potential energy equaling 0, for astronomical distances, okay, we set potential energy equal to 0 way far out away from us. We set potential energy equal to 0 at infinity. The key was that as the masses got closer, whether you're talking about near Earth's surface, okay, or if you're talking about two things that are really far away from each other, okay, as the masses get closer, okay, so I said this is 0. When this gets closer, the potential energy goes down as masses get closer. So now, as these masses, let's say, attract each other here, okay, as they get closer, the potential energy goes down. Well, if you start at 0, if you start at potential energy at 0 when they're infinitely far apart, okay, that's where we get a negative potential energy. And I should use actually U. Okay. Potential energy due to gravity is negative when we're talking about astronomical distances. Okay. Sorry for mixing up PE and my U's, but I'm going to try to use U from now on. Okay. So now, when we talk about the electric field, okay, we want to follow the same concept as we're using for gravity. When charges are infinitely far away from one another, okay, we're going to say that the potential energy is equal to 0. So now if I have two charges that are really far away, okay, we're going to set that potential energy equal to 0. Not that hard to follow, okay? It's going to be a little bit different, though, from what we see with gravity, okay? So if I start off with them really far away, I'll start off with 3 charges here, okay? And we're going to say that these are infinitely far apart. Obviously, they're not actually infinitely far apart. They're just a good distance away. We say that the potential energy is equal to 0. Well, we bring those, and this will be some sort of initial state. I. Okay? Well, now I bring those charges much closer together, okay, to some sort of final state, which I'll just call F. Okay? This will have some non-zero potential energy. We're going to say that the work done in moving them in from infinity, okay, this W infinity here, that's a work done in moving these charges from a really far distance apart to this distance here. And it's a work done by the electric field. Okay, I want to be very clear about that. It's a work done by the electric field in moving these charges in from infinity. Okay, so now, what we're going to talk about here is the absolute potential energy. Absolute potential energy, we'll note here, absolute. Okay, the absolute potential energy is the energy to bring them in from infinity. Okay? So sometimes you'll see it like U, that will equal potential energy and bringing them in the change in potential energy and bringing them in from infinity. Now, when we talk about gravity, two masses that are really far apart with gravity, this one has M1, this one has a mass M2. As these masses, and they're just released, and we look at the work done by gravity in bringing these two together, okay? The force of gravity is going to go, it's going to be attractive. So we've got a force like this, D1, okay, that's going to bring us in that direction. Force of gravity over here, same thing, same forces. I don't have to call it D1 and D2 because they are the same. But the distances could definitely be different because the masses could be different. So now, they'll come together to some condition like this. Okay? So this would be your initial condition, this would be your final condition. So now, the work done by gravity here, okay, as the masses got closer, again, as we said before, as we bring those masses closer together, okay, the work done by gravity is positive. But the potential energy change is negative. Okay? Because as I bring the masses closer together, the potential energy goes down. Now, same could be true for the electric field. Let's take a look. If I have a positive charge here and a negative charge out over here, if I release them, okay, they're going to attract each other. So now I've got the force of the electric field going in. I've got the direction of motion, D, going like that. Call this D positive. Force is going to be the same, going in. Okay, the D negative is also going to be going in that direction. So again, the work done by the electric field is positive, and we have, therefore, a decrease, okay, in potential energy. The potential energy decreases as they get closer together. But the electrostatic force isn't always positive. Okay? So to the point when they get like this, this would be your, again, your initial state, and down here you add your final state. Okay? The electrostatic force doesn't have to be attractive. If I have two charges here, one positive and the other positive, it's not making them quite infinitely far apart. Okay? These two are going to repel one another. So it'd be more interesting to start off with them closer together. So if they start off close together from positive here, this is my initial state, they're going to repel one another. Now, so these two would repel one another. So now, in this case, when they get further apart, actually, let's go back. I should edit this. It's positive here and positive here. These two are going to repel each other. So my force is going away. But let's say that I have some actor, some cosmic actor that can stretch its arms out infinitely wide, so that it's going to bring them together. So my direction of motion, D, goes in. D positive, whatever. Okay? As they get closer together, the force due to the electric field is trying to oppose this. So as they get closer together here, this is my initial state, this is my final state. Okay? The work done by the electric field in this case is negative. And despite the fact that we brought them closer together, my potential energy change is positive. So potential energy is increasing as I bring these two closer together because the force is repulsive. Think about it this way, okay? As far as your change in potential energy. If I took these two charges right here, and I released them from rest, they're going to smash into one another, okay? Coming in from infinity, they're going to smash into one another with some sort of velocity v. Would they hit each other faster if they started from here, or if they started from some non-infinite distance? Okay? They would smash together faster if they're almost infinitely far apart. That's why we say the potential energy is greater. Okay, out here. okay? Because from right here, you're not going to get that as large of a smashing. Same thing here with the charges, okay? Because it's attractive, the faster, okay, the further apart they are, the more potential energy, the more kinetic energy they will have when they smash into each other. So that increase in kinetic energy comes from the potential energy. Now here, okay, if I have these two really far apart and I release them, okay, there's not an awful lot of force between them. So they're not going to get spread apart very quickly. But these two are starting really close to each other. So if I release these, the change in kinetic energy is going to be a lot more because they're a lot closer together, there's a lot stronger force. Okay? So we have a greater potential energy here and a smaller potential energy here. Okay. Now, all right. Moving from potential energy to electric potential. With electric potential, okay, think about the electrostatic force. Okay, we know that force is equal to 1 over 4 pi epsilon naught Q over r squared. So if I have some large positive charge Q here, and some little test charge Q, little q here. Okay, the force that's acting on this little charge Q, okay, is going to be that 1 over 4 pi epsilon naught, or K, QQ over r squared. But now, a field is set up by this charge, and actually by this charge too, but it doesn't feel its own field. A field is set up by this charge, okay, so that I can predict, if I know the field, I can predict the force on that charge, regardless of what charge it is, and regardless of how far away it is. Okay? That field, that electric field, is going to be the force per unit charge, and that's going to equal K. Do the capital Q here. So K, I'm going to use 1 over 4 pi epsilon naught. Big Q over r squared. Okay? So if I wanted to figure out what the force was, I plug in whatever the charge is, okay, and I multiply by 1 over 4 pi epsilon naught Q, divided by whatever that distance is squared. Okay, so I can figure out what the force is very quickly. Now, we have a similar thing for the potential energy. Okay, we have what's called electric potential. And instead of looking at the potential energy, a lot of times it's more convenient to look at electric potential. So now, at some location, we find that the potential energy on a proton. So we have a little proton here, a little P positive. Okay, that's equal to, the charge on it is equal to 1.6 times 10 to the minus 19 coulombs. So now, at this location right here, a little proton, okay, I find that the potential energy on that proton is equal to 2.4 times 10 to the minus 17 joules. Okay? It is still potential energy, so it's still measured in joules. Now, interestingly enough, at that same location, if I measured it, the potential energy from two protons. The potential energy from two protons is equal to 4.8 times 10 to the minus 17 joules. That's interesting. I doubled the charge, I doubled the potential energy. Let's take a look at that potential energy per unit charge, okay, for the one proton.
Why do you go from joules to coulombs?
Oh, sorry. Thank you. Joules, big time. Now, potential energy per unit charge, okay, was for the one proton okay, was 2.4 times 10 to the minus 17 joules over 1.6 times 10 to the minus 19 coulombs. So the potential energy per unit charge for the one proton was equal to 150 joules per coulomb. Okay? So now, for the potential energy for two protons per unit charge was 4.8 times 10 to the minus 17 joules divided by, now it's not going to be 1.6 times 10 to the minus 19. I have two protons, so it's going to be 3.2 times 10 to the minus 19 coulombs. So my potential energy per unit charge here is equal to 150 joules per coulomb. Okay? It's the same thing. So now, what we call this potential energy per unit charge is what we call electric potential. And we use the symbol V. Okay? V will equal potential energy per unit charge. Okay? Taking a quick look at the units for potential. Units for potential energy are joules. Your charge is coulombs. We've named this after a famous scientist, Alexander Volta, or the volt, not the car, the it. So now, a lot of times we don't care about the absolute potential V there, we care about delta V. Delta V will equal V final minus V initial, which will equal U final, potential energy per unit charge final, minus potential energy per unit charge initial, or delta U Q. So now, along with that now, we know that work is equal to negative delta U. So delta V will equal negative work per unit charge. Okay? And this is work done by the electric field. So we can say that the work done by the electric field is equal to negative Q delta V. That's work done by the electric field specifically. If you're looking at absolute potential, okay, absolute potential, we're talking about the work moving it from infinity, okay? And so delta V, or V, because V in it would be 0 for at infinity, and negative work moving it from infinity per unit charge. Now, and that's absolute potential. Okay, just a few more things here. We want to talk about more conventional unit for the electric field. The unit for the electric field is equal to a Newton per coulomb. Now, along with that, we know that 1 joule is equal to 1 Newton per meter. So I could, I'll just move 1. It's a Newton per meter. So now, excuse me, okay, let's get confused with K with springs. So now, a Newton can be rewritten as a joule per meter. So let's take that into account. The unit for the electric field will equal a Newton, which is a joule per meter, meters times coulombs. But take a look at this. What's a joule per coulomb? volt volt, okay? So we'll get it for the electric field. More conventionally is written as volts per meter. So from now on, we'll pretty much work, unless we're talking about force specifically, we'll talk about the electric field having units of volts per meter. So now, one thing, well, I'm going to hold off on work done by the applied force. I do want to talk quickly about equipotential surfaces. Okay. Think about this. I have a certain amount of potential energy above this table right here. Okay. Where else would I have the same amount of potential energy? What would define having the same amount of potential energy as right here? How about right here? Would that be the same potential energy? How about right here? Approximately. Okay, it's about the same. Okay. Anywhere along this height, over this desk, I have the same potential energy. Okay? So it's called an equipotential surface. So now, if I look at gravity, here, okay, here's the Earth. Looking at gravity, anywhere that same distance from the surface of the Earth, okay, is going to have what I call this equipotential surface. Now, I can make another equipotential surface. Okay? If I go a little bit higher, anywhere along here, it's going to have the same amount of potential energy. Now think about this. Which way does gravity act? Gravitational field acts inward. Note the angle between the gravitational field and the equipotential surfaces. Okay, put it at 90 degrees. Okay. Now we actually are going to do a lab in class on this. We'll probably do this on one of your days that you guys come in at 9 o'clock. Okay. The electric field. If I have an electric field, nice horizontal electric field, constant electric field, which would exist between two plates. So my electric field points like this. There's my E field, in blue. If I start off here, and I go to here, somehow, from my initial point to my final point, as I go from here to here, okay, I've moved along with the electric field. The electric field has done work on it. Anywhere along here, okay, the gravitational field hasn't done any work. Okay, if I hold this pen up here like this, okay, gravity points down. I move anywhere along this horizontal surface here, okay, the direction of motion is always perpendicular to the gravitational field. Okay, so I do no work anywhere along this equipotential surface. When I go like from here to here, okay, when I'm right here, okay, the electric field is going to produce a force that goes in this direction. Okay, electric field right here is going to point in this direction, while my direction of motion, call it S, ds here. Sorry, a little too small. My little ds there, okay? It's not, you don't have 90 degrees, okay? So that's not going, between here and here I don't have an equipotential surface because I'm doing work. The electric field is doing work. But if I looked at a point over here, and I go from here now to this final point, at no point along there, okay, does the electric field do any work. This is an equipotential surface. moved along an equipotential surface. Again, thinking back to over there, okay, if I want to do no work, okay, I move horizontally, I move perpendicularly to the gravitational field. If I want to move so that I do no work due to the electric field, okay, I'm going to move perpendicularly to the electric field. So my equipotential surfaces, okay, called V equi, okay, are going to be perpendicular to the electric field. It would look like that. One thing that I want you to prove to yourselves, instead of making a path like this, I start off here and I start off here. When I do it crazy, it's kind of hard to prove. If I go like this, start off here, I go down here, and I come back here. Try to convince yourselves of the fact that the work done by the electric field is zero across it. Okay? Instead of following the straight path, I do kind of a zigzag. Try to convince yourselves of the fact that you're still going to do no work because you start and end on the equipotential surface. That can be a little bit harder to, and I want you to do that with a question.
So it's like a state, almost like stateless functions or whatever,
Yeah,
where it doesn't matter how you get there.
correct. It's not going to matter how you get there. That's kind of that's a big thing. It's going, the work done by the electric field will equal Q delta V, regardless of how you get there.
So it's just like how if you come up to the other side of a hill from a hill and you go across a valley, potential energy doesn't change.
Correct. And the work that you would do is
Is
actually
zero.
zero, because gravity does work on the way down. You're doing, and it does negative work on the way up.
Yes.
Okay, now, what I want you to do, one thing to do in addition with your homework, okay, is going to be, let's just say I have a positive charge here, okay? I want you to draw the electric field and 3 equipotential surfaces. Okay? And then I want you to do it, and I'm going to post the homework on the website. I want you to do for this, positive, negative, I want the electric field, and this time I want 5 equipotential surfaces. Okay, that one's a little bit more interesting. This one, not so much, just gives you a feel. This one definitely a lot more interesting. Okay, now, for section 24.6, the potential due to a point, due to a 24.5, excuse me. Okay, calculating the potential from the field. My electric field is going to go like this. Okay. I'm going to take, a charge here, and it's going to follow a path to here. This will be my final point. This will be my initial point. Okay. I'm going to call that path S. Okay, path S. Now, looking at the work that's done on it, when I'm right here, okay, the direction of the electric field is going to be about that direction. So here's my E. My path S, my little ds, is going to go like this, okay, following along the path. That'll be my ds. Okay, sorry if that's a little faint. Better red marker. Okay. So I've got something that looks like that. Now, the reason why that's important, the work that's done by the electric field, the work done at this little point right here, so a tiny little amount of work is going to equal the force times dotted with ds. Now the force is going to be in the same direction as z, assuming that this is a positive charge. That force will equal E dot ds. Okay? QE dot ds.
That makes much more sense.
Okay? Yeah, E doesn't make a whole lot of sense. Q makes a lot more sense. So if I want the work done, okay, I've got to integrate. I'll put the Q out in front. Integral of E dot ds. Well, now, I know that potential, and this is going to be from my starting point, initial, to final. Well, now, potential, okay, my delta V, really, okay, is going to equal the work done per unit charge in a negative. So now, if I divide both sides by Q, I get work divided by charge, which is potential with the negative. So my delta V here will equal negative the integral from my starting location to my final location of E dot ds. Okay? And that's a big one. Okay? That will be helpful for us. Now, the thing about this, okay, this is what's called a line integral. Okay, that ds means that you have to follow along the path. Have you done line integrals in BC?
Name doesn't sound familiar, but
Okay.
I'm sure we'd have done something similar.
Well, you'd have to calculate what this path is along here. You'd have to come up with an equation for that path. That would be very hard.
Okay.
This is very nice because it's a conservative force. We don't care what the path is. Technically, it's a line integral, but we can choose any path that we want. So we choose the most convenient path, which would be a straight line from your starting point to your end point, which is much easier. Okay, and that's because the electric field is a conservative field. Okay, so that will not be as bad as what it may seem at first. Okay, and we're going to take a look at a condition right now. We're going to look at the potential due to a point charge. We're going to make use of this equation. And then we'll end it here. Potential due to a point charge. If I have a positive Q right here, okay, and I have some point right here that's we'll assume some small positive test charge. Remember, test charges are always positive. Okay. And I want to look, I'm going to look at what's called absolute potential. We're going to look at the potential due to this, absolute potential due to this point charge. I'm going to move this off towards infinity. It's terrible. So now, the force on this is going to be positive. My ds, okay, I'm going to move this out towards infinity. My ds is also going to be going up. Okay, so now, looking at this, okay, that force will equal EQ. So now, looking at the E dot ds, okay, it's going to be moving in the same direction, so I'm going to wind up with E ds. Okay. By convention, because this is along a radial, okay, it can go out in any direction, because this is radial, we use dr instead of ds. So what I wind up with here, okay, is that my delta V is going to equal the integral, negative integral, from some distance r to infinity of E dr. So now I'm going to rewrite that. Delta V is going to be V final minus V initial. Integral negative from R to infinity. E is going to be 1 over 4 pi epsilon naught. Q, big Q, over R squared. That's E times dr. So now, Q is a constant. 1 over 4 pi epsilon naught is a constant. V final, my potential at infinity, I already said was 0. So that's 0, so I get negative potential is equal to negative, I'm going to go from R to infinity. Let me just pull the constants out. Q over 4 pi epsilon naught, integral from R to infinity of dr over R squared. Negatives drop out. Vi I'm just going to call V. Okay, integral of 1 over R squared.
Negative
dr.
1 over R.
Okay, negative 1 over R. So I get negative Q over 4 pi epsilon naught, 1 over R from R to infinity. So my absolute potential is Q over negative Q over 4 pi epsilon naught, 1 over infinity minus 1 over big R. This goes away to 0. 1 over infinity is 0. I have negative Q over 4 pi epsilon naught times negative 1 over R. V is equal to positive 1 over 4 pi epsilon naught Q over R. Now, this is the potential due to a point charge. Notice, by the way, that potential is inherently a dot product. It's not a vector. Okay? What's nice about things that aren't vectors, you can just add them. So the potential due to a group of point charges, due to multiple point charges, I'll just say n point charges is going to equal, I'll say n equals 1 to I guess whatever. It's going to equal potential energy due to 1, potential due to 1, potential due to 2, plus potential due to 3, dot, dot, dot. Okay? There is no vector adding. It's just driving potential. Okay. All right. That gets us through a big chunk of the chapter. Some harder stuff is ahead. And with calculating 24.9, calculating the potential due to a continuous distribution of charge. We're not going to spend a whole lot of time on that, but we do need to take a look at it. So anyway, I will leave you with that, and I will see you on Friday.